It's 5:30, so let's go ahead and get started. Good evening, everyone. How's everyone doing today? Good, good. It's good to be back. And so thankfully, so my fiance tested negative for COVID twice, and so she's all good. She was coughing really bad last week, so I was a little bit worried for her, but I think it was just some kind of bronchitis or something like that. So she's still kind of getting over it a little bit, but she's definitely a lot better than she was last week. So I decided to come back. Okay, and so this week is kind of a special week, and so this is another ANSYS week, and so we have a ANSYS activity plan for Wednesday, and it's basically going to show off the dynamic simulation capabilities of ANSYS. Okay, and today we're going to be doing the accompanying lecture, so just talking about kind of what dynamic simulations are, what situations they use them for, and what are some kind of key concepts for them. Okay, and so my plan was for kind of this Monday and Wednesday to kind of be paired. And so I know we didn't really finish the advanced meshing stuff last Wednesday, but we're going to pick that up next week when we have kind of a full lecture week. But I want to make sure that we talk about some transient simulations before we try it out on Wednesday. Okay. All right. So remember, your activity 4 is due this Wednesday at midnight. Okay. So make sure you're working on that. It is I think probably the longest assignment that we've done so far. So make sure you're getting started on it. And if you run into any issues with it, definitely let me know, and then we can kind of work through them together. Okay. And your midterm project is going to be due next Friday. Remember that. Okay. So make sure you're working on that as well. And so the activity 3 or the activity 5 that we're going to do this week, I'm going to push that due date to be due. I think right now I have it due 2 weeks from Wednesday, but I'm going to go back. I'm going to push that back a couple more days and have that be due on Friday. I believe it's November 7th. Just because I know that probably up until next Friday, I think everyone's just going to be working on the project, and so I want to make sure I give you a full week after the project's due to work on this activity. Okay. So next activity, and we'll talk about this on Wednesday too, is going to be due Friday. I think it's either November 5th or November 7th, but the first Friday of November. Okay. I do want to make an announcement too that this Friday and most of this weekend I'm going to be unavailable because I'll be flying to Columbus for a friend's wedding, and so I'm flying out on Friday, and then I'm going to be going to the wedding and stuff like that, and so just to kind of make you aware. So if you have questions on the project, try to get them to me before Friday, and then I'll be able to answer you. But of course, I'll be back next week to answer any questions too. It's just this weekend, I'll try to answer some questions maybe early on Saturday. But our plan right now is to kind of be out kind of the whole weekend, and so I'll be relatively unavailable this weekend. Okay. All right. So are there any questions I can answer before we get started today? Okay. All right. So let's talk about dynamic simulations. All right. And so up to this point in the class, we've really just been doing static simulations, right? And so basically, the main thing with statics is that nothing is changing with time. Okay. And so that's fine. And so, there's a lot of engineering situations that don't change with time. And in fact, for a lot of engineering situations, I would say is that you don't want things changing with time. And so you don't want like your building structure, your bridge structure to change, deformation with time. That would be kind of scary. Okay. And so, with static analysis, there's already so much work that you can do. And so, just that by itself is already a great amount of tools in your toolbox that you can take to so many applications. But with that said, there are a lot of problems that actually do change with time. basically any kind of situation where you have a moving part. Okay. And so a lot of machinery falls under this category. We have just kind of parts moving as part of a mechanism. Okay. Any kind of impact situation, which is what we're going to do on Wednesday. And so we're going to be simulating a car crash, right? And so anytime you have something impacting another one, then you're going to have the deformations and the stresses changing with time. That's another situation. Okay. And so for these kinds of problems, you can model them as a static problem, and so you can do what's called like a pseudo-static simulation, but it's never going to be exactly right. And so in order to really simulate these situations that change with time, you need to run what's called the dynamic simulations. Okay. Because one thing that dynamic simulations will allow us to do is it allows us to actually play with this time parameter, right? And so if you have a boundary condition that changes with time, if you have a structure whose geometry is changing with time, if you have a mechanism, right now that's not possible to do in statics, but in dynamics you can actually do that. Okay. And so it's a whole nother type of analysis, right? And so for the first time in this class, we're not going to be using static structure. So we're going to be doing something else. Okay. And so the good thing is that FEM, it can handle these dynamic situations, no problem. But the theory that goes into transient simulations is almost completely different. It's kind of its own field. Right? And so I will say that the amount of time that we're dedicating to transient simulations is extremely small, right? And so you can take entire classes on steady or dynamics types of simulation, going all the way back to like the straight numerical methods. And so, we're barely scratching the surface. And and I know I say that about a lot of things in this class, but for dynamic simulations, it really is. Because I remember when I was in school, like I took a good 2 or 3 classes just on effective methods for doing dynamic simulation. And so we're doing just 1 week. And so I think 1 week is enough just to give you the basics and just to make you aware of that it exists. But if you really want to dive into the theory and really dive into all the different kinds of issues that can happen, you need full classes for that. Okay. Because the issues that you have with dynamic simulations, it's kind of a whole nother set of issues. Not that they're any more challenging or any more or any more difficult than the challenges that you've all been facing so far. They're just different, and to learn how to deal with all those issues, you really need a kind of a good understanding of everything. And so we're going to go nowhere near all those issues and everything that can happen. We're just going to do just kind of the absolute basics of dynamics. Okay. But if you are interested in learning more, the class that you would take is something called numerical methods. And we do offer that here. It's not an EGME class, it's an EGGN class. So it's a general engineering, and I believe it's EGGN 403. I've been begging the department to let me teach this class for years now, because it's one of my favorite classes ever. But because it's general engineering, it's assigned by the dean's office, and I guess the dean doesn't like me, and so I've never gotten a chance to teach it yet. But hopefully I'll get on her good side, and she'll let me teach it sometime. Yeah.
Do you know if this class counts towards our degree, or we're even allowed to take it if it's in the general engineering department?
It should, because it's a 400 level class, and so it should count as one of those 400 level. I think grad students have taken it before, but I would definitely double check with the advisor just to make sure. Yeah. But my understanding is that any 400 level class can count for grad degrees. Okay. So any questions on this so far? Okay. And so to kind of motivate the theory behind transient simulations, we have to talk about the lumped mass model, or in other words, called the mass spring damper. This is kind of a good historical lesson too, because kind of before the age of finite element simulations, which wasn't really that long ago, which is relatively speaking, maybe like 50, 60, 70 years ago, people still design structures that moved, right? So people still design cars, they still design, machines that move, right? And so, this is kind of a little bit of a historical lesson of how people design dynamic systems before FEA. And I'm going through this because I think it gives a lot of good intuition for how these, not just for FEA, but how dynamic systems behave just in general, okay? All right. And so this mass spring damper, I consider this to be probably the simplest dynamical situation that you can have that accounts for all the major behaviors. Okay. All right. And so the mass spring damper consists of just a mass, a spring, and a damper. And so there's lots of ways to draw it, but I think this is probably my favorite way to visualize it. Okay. And so on one hand, you have a spring, and so the spring has a spring constant K. Okay. On the other side, you have a damper, and so that has a damping constant called C. Okay. And those two act in parallel. That's why I kind of drew them like that. Okay. And on the right here, you have a mass M. Okay. And it's being pulled by a force F. Okay. All right. And so let me go ahead and label all the parameters here. So K here is the spring constant. M here is the mass. And C is the damping constant. And F here represents some kind of external forcing, okay, which could change with time. All right. And so the nice thing about this particular system is that once you pull on the system with the force F, you can either pull or you can push it. Then the position of the mass block is going to change with time. Okay. And so if we basically take the displacement of the mass block, we call that x of t, right? We can form a differential equation in time that solves for the position of the mass block, right? All right, and so that ODE looks like this. Okay, so you have m times the double derivative of x with respect to t, okay? And so you'll probably recognize this as m times a, because the double derivative of position is acceleration, okay? Then we have the damping term, and the damping term is proportional to the velocity, okay? It is a dx dx, it should be dx dt, sorry about that. Okay. Then we have the spring term. And so the spring term is going to be our spring constant K multiplied by X of T. And this is all equal to our external forcing F of T. And so hopefully, this system here looks familiar. And so if the mass spring damper wasn't familiar, then hopefully this differential equation is, because this is the classical kind of second order ordinary differential equation. And so I think this is used in physics classrooms, it's used in math classrooms, it's used in applied engineering mathematics classrooms. And so, this is a very, very classical equation with very, very classical behavior that, we can use to characterize a system. Okay. All right. Any questions on this? Okay. All right. And so, because we have a differential equation here that changes with time, then we know our solution here is going to change with time as well. Okay. And the behavior of that solution is actually going to depend mostly on the values of our different parameters here. Okay? So depending on M, depending on C, and depending on K, those are going to determine what our solution ultimately looks like. Okay? And there's a lot of different cases that that you can look at, depending, and a lot of it has to do with the relative strength of the damping of C compared to M and K. Okay, but most physical systems and kind of the focus for this class is we're going to be looking at underdamped situations. And so in underdamped situations, the damping constant is relatively not going to be as strong as the mass or the spring constant. Okay, and so that gives rise to a time solution that that oscillates with time. Okay. Okay. And so for an underdamped solution, basically, if you took your mass spring damper here and you kind of struck it with the hammer, and so we provide kind of an impulsive forcing, then it's going to cause the mass block to kind of rotate kind of back or oscillate kind of back and forth. Okay. And so in this situation, the solution takes the following form. Okay. And so if we say x of t is equal to a e to the minus bt times sine omega t plus phi. Okay. And there's two aspects of this solution that I want to highlight. And so first is this guy. Okay. And so this first part right here, this is what's known as the exponentially decaying amplitude. Okay. And then the second part right here, this is our oscillatory component. So this is the part that's actually going to oscillate up and down. Okay. All right. And so if we plot the solution, so let's say that, we make a plot like this. Okay. Where on the x-axis here we have time, and on the y-axis here we have x of t. Right. Our solution is going to look something like this, where our amplitude is going to start really high, and eventually it's going to decay down to 0. Okay. And so this is kind of the general kind of oscillatory solution that you can expect from a mass spring damper. Okay. And this is pretty typical for a lot of mechanical or structural devices. And so probably you guys have heard of vibrations, or you might have taken a vibrations class. And so the vibrations that you see in those structures are because of this expected dynamic response. Right? And in fact, I think it's activity, I want to say activity 6. We're actually going to be looking at in ANSYS, how do you do actually vibration analysis or modal analysis? Okay. And so we'll come back to this idea of vibrations at a different point in this class. But in general, almost every structure that you have is going to vibrate to a certain extent. Like if I took this overhead thing, I kind of smacked it with my hand. You can see, well, I can see because I'm right here, but the thing is actually vibrating a little bit, right? And so most mechanical devices will, or most structures will have this kind of underdamped behavior. If you guys smacked your monitors right now in front of you, then you probably see the same thing, but don't do it too hard because I get in trouble if you guys break the computers. But if you kind of lightly tap it, then you can kind of see that your monitor is going to vibrate as well. Okay? And so even though we have this kind of, it may seem like a very simplistic system, and maybe one that's far from reality, but it has a lot of physical characteristics that that we expect in terms of dynamic response. Okay. Any questions on this? Okay. All right. And so, what does this have to do with, what we're doing for transient simulations, right? Right. So remember what I said before is that the keys to this model here, assuming that you can kind of solve this solution by hand, right? The keys to this model are the values M, the values of C, and the values of K. Okay. And so, before the age of finite elements, what engineers used to do is that if they saw, if they were designing a certain structure, and they were interested in computing the dynamic response, they would actually use the mass spring damper. But the way they would use it is that they would look at their structure and complexities and everything, and assign values for M, C, and K based on the structure. Okay. Okay. Because you can imagine, before the age of finite elements and before the age of powerful computers, and you want to see how much your structure is going to vibrate or how it's going to respond dynamically, then they had to do it based on these models. Okay. All right. And so that kind of begs the question of how do you take something that's really a very complex structure and how do you boil it down into these kind of very simple parameters, right? And so let's go through each of them individually. Because these are good to kind of think about in general, where if you have kind of a general structure, what aspects of that structure are going to go into each of these parameters. All right, so let's start with the mass. And so the mass is I think the simplest. And so for the mass, you can just assign the mass of whatever structure you have. Okay. And so for the mass, there's very little approximation that has to be done there, or very little ambiguity. Okay. All right, spring constant. Spring constant is, relatively speaking, easy but it's also not very straightforward either. Okay, because the spring constant, if you think about a spring in reality, it's basically an elastic structure. Okay, and so the spring constant, in quotes, of just an arbitrary structure will depend on how elastic that structure is. And so what this means is that it's going to largely depend on the material properties. And so if you have a linear isotropic material, then this would depend on things like the Young's modulus and the Poisson's ratio. And so spring constant, relatively speaking, is easier because it's, I think generally everyone agrees that it depends on these things, but the exact relationship is going to be different. And it's going to depend on the geometry of your structure as well. Okay. All right. And so lastly, we have the damping. Okay. Okay. And so the damping, I would say this is probably the most difficult to estimate. Okay. And so for the mass and the spring constant, I'm relatively confident that I can give you a structure, with the material, and I can ask you, first of all, I hope you can tell me the mass. You can just kind of measure that within ANSYS. The spring constant, maybe it's not exact, but you can tell me whether the spring constant is really high. Maybe it's for a steel structure for a steel. And so for a steel structure, the spring constant would be pretty high for that. But if it's made of something really soft like wax, that's not going to be very elastic at all. Okay. And so, we can say with relative certainty what the first two are. Damping is a lot more difficult because this is determined a lot by the environment on which the structure is in, and it's also due to a lot of kind of micro properties within the material that are hard to measure. Okay. Okay. And so for before the age of finite elements, the way damping was usually determined was from data and observations. Right. But people did it before, right? And so they basically kind of did some trial and error, and they were able to come up with some good values for damping in certain situations. Okay. And so, just based on these three constants, and so basically if you can assign these three constants, then you can kind of, you can reasonably predict the dynamic response of a certain structure. Okay. And so, as we're kind of going about our dynamic simulations, especially, and I think this is really relevant for our car crash. I want you to kind of think in terms of, what are these three constants? Okay. Because and so what we're going to go over next is, how do these three constants, or how do these three parameters, how do they actually affect our dynamic response? Okay. All right. So any questions on this? Okay. Okay. And so let's go through each of them and see, right? And so this is the part that's kind of, all this is kind of to give you some intuition for how you can approach your dynamic simulations, and how do you approach, analyzing your results. Okay. All right, so let's start with the mass. So having more mass in your system will basically give you more inertia. And of course, the opposite is true. If you have less mass, you have less inertia. Okay. And if you remember, the definition of inertia is the ability for a structure to resist changes in motion. Okay. And so if you have more mass, then it's going to be a lot harder for your structure to change its motion. Okay. Okay. And so if you have something massive that's already in motion with a certain velocity, it's going to take a lot of forces. It's going to take a lot of work for that to change, to change direction. Okay. And so if this really massive structure is going to hit something, it's going to impact a wall, then that wall is going to take a lot of damage because, our mass was just so high. Okay. And so speaking mathematically in terms of a vibration response, and so the more mass something has, the slower the oscillation is going to be. Okay. Okay. All right. So the spring constant, the spring constant is going to have the opposite effect. And so a higher spring constant basically means that your material is going to be stiffer. And if you have a stiffer material, then the material is going to be quicker to react with this dynamic response. Okay. Okay. And so mathematically, in terms of our oscillating solution, a higher spring constant means it's going to increase the frequency of oscillations. Okay. And then last, we have the damping. And so the damping is going to affect how well your structure is going to suppress any vibrations or oscillations. Okay. And so the higher your damping, the quicker the magnitude of your, or the amplitude of your oscillations is going to go down. Okay. And so if we go back to the mathematical response here, right? And so this first term right here, which is the exponentially decaying amplitude, the only term that really has the big effect on this is the amount of damping. Okay. And so the more damping you have in your system, the more, the more quickly your oscillations are going to die. Okay. Okay. And so, of course, for a general, even the most simple, 3D dynamic situation, it's going to be a lot more complicated than this mass spring damper. And so, as we kind of go through, how to set these up in ANSYS, I still want you to kind of remember these three properties. And so, think about your structure in terms of its mass. What would its spring constant be? What is material properties? How much damping is there in the system, right? Because I think this will give you some good intuition of what you can expect from the response. Okay, because in the activity that you'll see on Wednesday, we're going to be simulating a car crashing into a wall, right? And so that's kind of an extreme case of like a mass spring damper, experiencing a huge amount of force at once. And so actually, if you run the simulation long enough, you'll actually see some oscillatory response. Mostly just because we don't have buckling turned on, and so what's going to happen is that the car is going to hit the wall. It's going to basically scrunch up, and then it's going to spring back to what it looked like, because we don't actually have material buckling activated. And so the whole car will kind of act like a spring. And so you actually see these kind of things in action, even though for this case it's not as realistic as probably as it could be, but you'll see all these three parameters in action. All right, any questions on this? Okay. All right, and so that's kind of the general intuition behind dynamic responses in general. And so now let's talk about how do we actually solve these kinds of problems numerically. Right. So in other words, how does a computer actually solve a dynamic situation, and how is this different than how a computer solves for a static one? Okay. All right. And so first thing I want to say is that compared to a static situation, a dynamic situation is going to be a lot more resource intensive. Okay. And so it's going to take a lot more time, first of all. And so you're going to be running your dynamic simulations for generally a lot more time than your static ones. It's going to take a lot more computer memory too. Although if you're kind of smart with how you write the code, it's not as big of an increase over the static case, but it can be a lot more, depending on how the method is implemented. But the important thing is going to take a lot more time. Okay? And the main reason for that is, if you kind of think about the difference between a still image, and so let's say that you take a picture on your phone versus if you take a video, right? And so if you take a still image, basically your computer just has to store just a single image, and that captures the whole thing. Okay? And so this is basically the same as a static situation. So because a static situation doesn't change with time, just taking a single snapshot is enough to capture all of the information. Okay. In other words, one thing you can think about is that you perform the finite element simulation once, and then you take a snapshot of the results, and then you're done. And so that's it for static. Okay? But videos, as you know, is not just a single snapshot, but a series of snapshots. Okay. And so kind of in the most naive sense, for a video that maybe consists of maybe 30 frames per second, right? Each frame has to be kind of stored individually, okay? And so if you kind of take that to the finite element analogy, right? Instead of just solving one simulation for one snapshot, if you need 30 frames to come up with one second of information, that means you have to solve your finite elements 30 times in a row, okay? And that's pretty generous. And so 30 times per second is actually not that fine. And so, a lot of times you're going to be working with a time step size that's a lot smaller. And so, you can basically think of it as you're solving finite element problems, over and over and over and over. And so, the cost for dynamic simulations can really get up there, especially if you're not careful with how you set the parameters. Okay. But that's okay. And so, probably what you'll see on Wednesday is that, you're probably going to be spending some time, waiting for your results to finish. And so don't panic. It's not, you didn't do anything wrong. That's just the nature of dynamic simulations, that they just kind of take a lot longer. Okay. Right. And so the other thing with numerical solutions to dynamic problems is that they kind of require a whole new set of theory in order to solve. Because the big difference here compared to statics is that we're now incorporating time into the solution. Okay. Okay. And so, of course, we're not going to get into those methods because that requires several weeks of lectures to really cover. But just know that they exist. Okay. And having time in your and the reason for that is having time in your differential equations is a much different beast than having space. Okay. Because up to this point, we've been solving differential equations, right? We've been doing static structural, and that's solving a differential equation. But when you do static structural, the only independent parameters in your differential equation are of space. Okay. And by space, I mean X, Y, and Z. Okay. Right. And so how you solve a differential equation with space is actually very different from how you solve one in time. And that's mostly with how things occur in space versus how things occur in time, which we'll talk about on the next page. Okay. But before I do that, are there any questions about this? Okay. All right. And so the thing with solving things in space is that you can solve things at different locations at the same time. Okay. Okay. Because the thing with space is that even though like let's say the deformation, right? And so even though the deformation of a structure at one location, of course, is going to depend a little bit on the deformation at another one. Because of the way the equations are structured, we can actually solve these at the same time, and that's totally fine. Okay. So let's say that we have a like an arbitrary potato here. Okay. We can solve for the deformation at this location and this location. We can solve them at the same time because of because of how space kind of behaves. Okay. And because of how the equations are formulated. Okay. With time, we can't do that. And so we can't solve for something that's going to happen 10 minutes in the future just right now, right? And so in order to figure out what's going to happen 10 minutes from now, or even just saying, if you wanted to predict what I'm going to say 10 minutes from now, you kind of have to know what I'm going to say, during those 10 minutes leading up to that point before you can kind of predict what I'm going to say, okay? And so the way that we say this kind of mathematically is that we say that time is a causal system. And so in order to solve for time at the next step, you need to know what happened at the previous step. Okay. Okay. And so that places a lot of constraints on how we can solve for the time equation, right? And so instead of in space, where in space we can basically solve for the solution at our finite element simulation everywhere at the same time, with time we kind of have to solve it one step at a time. And so we have to start with step 0, and we solve for the solution at step 1 and then step 2. Okay. And so it's a very sequential process. Okay. And so the category of methods, that are used for solving these unsteady situations is called time marching, because you're essentially marching forward in time. Okay. Causal. Okay. And so you'll hear the term time marching quite a bit, okay? Because you're essentially marching the solution forward in time, one step at a time, okay? Or another term that you'll hear is called time integration. Okay. And so they all kind of take the following form. So I will say there's tons and tons of different methods to do time marching. Okay. But they all kind of have the following form. Okay. And so basically what we're saying is that we have u at n+1. And so this is the solution in the next time step or in the next frame. This is going to depend on un, where u to the n power here. This is the solution at the current frame, at the current time. Okay. And this f right here just means that it's a function of these things. Okay. And so it's a function of the solution at the current time. It's also a function of all of the material and geometric parameters of your structure. Okay. And so thus your mass constant, your spring constant, your damping, et cetera, et cetera. Okay. Okay. And so all time marching schemes kind of follow this this trend right here, where it takes it takes a solution at the current time step, it combines it together mathematically with all the material parameters in your structure, and it uses that to make a prediction of the solution at the next time step. Okay. All right, and we're not going to go any more into that, because any more into it, then we're then we're transforming into a different class. All right. Any questions on this? Okay. All right. And so one really important parameter that you'll be setting, in your simulations on Wednesday, that's unique to dynamic problems, is what's known as the time step size. Okay. This is probably the most important parameter for dynamic situations, and all dynamic problems have this. Okay. And so what the time step size here, what it specifies is the amount of physical time there is between the frames of your dynamic situation. Okay. Okay. And so if I draw kind of a timeline like this, okay, and let's say that each of the dots here represents your solution changing with time, right? And so each of these dots here, that's a separate finite element problem that we're solving, okay? Okay. And so the time in between your frames right here, this is your time step size. Okay. And so sometimes, the symbol for time step size is given by delta t or dt. Okay. Okay. And so this time step size is something that the user yourself has to specify. Okay. Okay. And the way that you can think of the time step size, or kind of the intuition behind it, is you can kind of think of it as very similar to the mesh size. Okay. And so in that sense, if you make your time step size really small, a smaller time step size will mean that your solution is going to be a lot more accurate. Okay. And generally it's going to look a lot better too. Okay. And so think about watching a movie, right? And so the more frames per second that you have in a movie, that means the better the movie is going to look, right? Because the amount of time in between frames is a lot smaller, right? And so if you minimize the time step size, if you make it smaller, then you're going to produce a better quality animation, or better quality, approximation of your dynamic situation. Okay. But the cost for this is that, if you make the time step size smaller, then you're going to have to perform a lot more calculations to get your solution. Okay. And so it's just like mesh size, right? And so for the mesh size, you make your mesh size smaller, then your solution gets a lot better, but you have to pay for that in some way. Okay, so the time step size is the same thing. Okay. And so on the converse side, if you increase your time step, Okay. If you increase your time step size, you're going to get a cheaper solution, and so you're going to get a solution faster. Okay. And for dynamic simulations, sometimes that's really significant because the cost is already going to be really high. And so if you can cut down on that cost, that often saves you a lot of time. Okay. But of course, if you make a larger time step size, you have generally a poorer quality solution. And also, the whole thing might just blow up. Okay. And so there's kind of an added risk in dynamic simulations called divergence. Okay? And so when your simulation diverges, what basically happens is that all your solution variables just tend to blow up. And so for the deformation, you get like 80 cajillion million. For the stress, you get bajillion million. And so you get numbers that are obviously way too high for what your simulation is. And in the worst cases, you might get even infinity, or the worst offender, NAN. Right? And so if you've used MATLAB before, you might be familiar with the idea of NAN, but NAN is basically what a program will tell you whenever you essentially you divide by 0. Okay. And so if you're not careful with your time step size and you make it a little bit big, you might get NANs in your solution. Okay, and that's obviously not correct. Okay. And so again, we're not going to go into the reasons or how divergence happens or why it happens, but just know that it can happen if you make your time step size too big. And so if you are running into NANs in your dynamic solution, the first thing you should try is try lowering your time step size and see if that helps. Okay. All right. Any questions on this? Okay. All right. And so I think that's kind of a good intuition to have with the time step size, but it's not really that useful for say that you're running a dynamic simulation for the first time. And so what should you set for the time step size just to start out, right? And so we kind of need a good reference point for this. Okay. And so the unfortunate thing is, the time step size is one thing where it's hard to make general rules for it because it depends on every single situation. But there is kind of a nice rule that the book kind of gives, and I had never heard of this rule before, but I think it makes a lot of sense to me. Right? And a lot of it is based on back on our mass spring damper. Okay, because remember what we talked about before, that a lot of structural systems, they're going to have that vibration or oscillatory type of behavior. Okay. Okay. And so if we have oscillatory behavior, then we know that the oscillations are going to happen within at a certain frequency a lot of the times. Okay. Okay. And so let's call this frequency f. And so let's say that you can determine it. Okay. And you'll see that f is actually not that hard to determine because it's a lot of times you can just set it to be like the natural frequency for your system, which we can find out very easily with ANSYS. Okay. And so the time step size that you should set, given that given that you have some knowledge of the frequency of your response. And so one good rule of thumb that you can do is you can do 1 divided by 20 times the frequency, and then that's a good starting point for your time step size. Okay. And so what this basically says is that because basically the frequency basically says how long it's going to take for one full oscillation or one full vibration to occur. And so by making the time step size this, then what we do is we make sure that we capture 20 frames of that vibration. Okay. Okay. And so this is a pretty good rule of thumb that you can use for especially for vibration problems, which is for a lot of the finite element applications of the dynamics, a lot of those are going to be vibrations, and so this is kind of a good rule of thumb that you can use. Okay. Okay. Any questions on this? Okay. All right. So the last thing I want to talk about for the last 15 minutes today are the two methods within ANSYS to solve for dynamics problems, because there's more than one. Okay. And so in ANSYS, you'll notice that there's a technique called transient structural. And the other one, which is what we're going to be using on Wednesday, is called explicit dynamics. Okay. And so let's talk about the differences between them and what situations where you would use one or the other, because they're both good, and so you can use them both for dynamic situations. But because of the way each of them are implemented, one's better for some things and the other one's better for the other ones. Okay. And so actually, let me give you kind of the situations where one is better than the other one. Okay. And then we'll spend the rest of today talking about the reasons why. But because we're a little bit short on time, I want to make sure I get to kind of the punchline first. All right. And so transient structural, this is usually best used for situations which don't change with time all that quickly. Okay. Okay. Because the thing with transient structural is that on a per time step basis, per time step that it solves for, transient structural is going to be more expensive. Okay. And so you want to use transient structural on cases where you're not going to run that many time steps. Okay. And the reason it's more expensive is that the transient structural is almost, I want to say almost, it's not impossible, but it's almost impossible to diverge. Okay.
That's it. More expensive on a, what was that part right there?
It's on a per time step basis. So basically each frame that you solve for, each frame is going to be more expensive in transient structural. And so because of the way transient structural is implemented, it's almost impossible for your solution to get those NANs, which is actually really, really nice, because that's one thing that I think will frustrate a lot of people at first when they're running dynamic simulations, that they get divergent solutions, they get unstable solutions. And so this feature of being able to almost always prevent that from happening is really nice. But it comes at a big cost because it's it is generally a lot more expensive. Okay. And so the textbook actually gives you a threshold for this. And I don't know if I necessarily agree with this because I think it depends on the situation. But if what the textbook says is that if your time step size is greater than or equal to 1 millisecond, then this is usually a good situation to use transient structural. I'm not sure if I agree with this because I think it depends on the situation and how many time steps you need to actually simulate it. But if you want kind of a numerical threshold, then that's kind of a good one to use. Okay. And so that's transient structural, and so that's the one we're not going to be using because the situation that we're solving for, which is a car crash, that's something that happens really quickly. And so for that one, in order to capture everything, you need a really small time step. And if you try this with transient structural, you're probably going to be sitting at your computer maybe for an hour or something like that. And so explicit dynamics is good for that. Okay. All right. Any questions on this? Okay. And so explicit dynamics. Okay. And so the thing with explicit dynamics is that you run into the risk of divergence very quickly. Okay. Okay. And so when you use explicit dynamics, you have to make sure your time step size is sufficiently small. And that actually doesn't have much to do with what's happening physically in your simulation. That's just how explicit dynamics is formulated. And so, even for a not so violent situation, if you use explicit dynamics with a time step size that's fairly big, you run the risk of diverging pretty easily. Okay. And so no matter what, with explicit dynamics, you have to use a small time step. Okay. But because we have the risk of diverging, then the amount of cost that you have per time step is a lot less for this one. Okay. And so explicit dynamics works really well for situations where you would want to use a small time step anyway. Okay. And those kinds of situations, question. So what do I mean by less cost? It just takes less time to simulate, right? And so let's say that you're running a dynamic simulation with explicit dynamics. And so per time step, it might take maybe on the order of, let's say, 1 minute to solve each time step. Okay. But if you ran the exact same thing with transient structural, it might take you 5 or 6 minutes per time step to run each time step. And so if you're running a simulation with even a modest amount of time steps like 100, then you're looking at the difference between 100 minutes versus 500, 600 minutes, and so that can be pretty substantial. Yeah. Mm-hmm. Okay. And so the situation that we're going to cover on Wednesday, which is a car crash, any kind of impact situation is going to happen really quickly, right? And so it's you basically blink and it's over, right? And so because of the situation that we're looking at is already something that we want to use a small time step, then it makes a lot of sense for us to use explicit dynamics for this one, Because, you know, one, we want a small time step anyway, just to capture all of the behavior. And two, you know, because we're using that small time step, then we're not going to run into the risk of divergence. Okay. 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 So now we're at kind of a weird spot. We're kind of explaining why this is, what I think will take longer than 5 minutes. And so I'm considering just kind of ending this here because it's because this is kind of the important thing I want you to know between the difference between explicit and transient, transient structural, and kind of the reason why and the analogy I think would help, but I think it also kind of ruins the message a little bit. So, and so are there any final questions for me today? Okay. All right, and so I don't want to go any further just because I think, you know, I want you to kind of, you know, leave with this. And so I'll stick around for a few more minutes if you want to ask me questions on activity 4, or if you have questions on the midterm project. But if not, you guys are free to go. So thank you guys for tuning in today. On Wednesday, when we meet up, we'll be simulating a car crash in ANSYS. And so hopefully that'll be fun for you guys. All right. So have a great evening, and I'll see you on Wednesday.
Hello,
Sure.
Professor.
Yeah. You have to supply some kind of constraints. So right now, you can see you have motion, so you have gravity, you have pressure, but you need to fix the structure. Without any constraints, the structure is yeah, so you just need at least one. So you can do both ends. It really depends on the situation. Yeah, usually when you get this this warning, is that it's under constraint. So you do that. Okay. Yeah, I think that's I think that'll cover 2 situations. So under that, you're basically just changing the pressure and changing. And so I think that's good for 2. But for the third one, I want you to think about, you know, what other types of load can you and so you can be creative a little bit. And you can think outside the box. So even if it's not likely to happen, so you can even do like Superman punching. And so really, you know, with finite elements, anything is possible. And so you can do similar. I think this is good for scaling. I think this is good because it's carrying through the portion of pressure. So I think that's a good start. But yeah, this one you just need to for your other loads. Okay, great. Yeah. Yeah. I would think that it was great because you're still someone's still trying to. So that's it.
I'm not feeling today. What are you gonna work on? I finished it. I had some weird
Either whatever.
results with the solid on.
Yep.
Don't use beams. That's not giving you
So
what I did.
yeah, so generally, so I think what's happening is that for this one you have to swap. And so the target is really particular. So the target that one is just slightly, whichever one is bigger. Bigger. So the face and generally a surface is going to be bigger. And so you can
My thing, like I guess apparently my constraint Like apparently there's a piece when I was just setting it up. Yeah, apparently there's a piece of the bridge that has a weird overhang on it. So like if you put the displacement on
Oh,
that,
yeah.
it fucks up all your shit.
So
So I didn't know. Okay. So I just had to swap sides, but I did that this afternoon.
Yeah.
So like I haven't really, I just
I
was
think,
like
so what I've been
setting
suggesting
up all my
is that you
mesh.
should
I was doing the
download,
mesh
when you download the
conversions
student
bullshit.
one, it just
So, like, I
automatically,
need to,
the website just goes to the R2 version.
Put that in
And so, but I think you
Excel.
can download
Do
the student
that,
version
and I
for
gotta do-
2021.
And then I gotta do
So
stuff
do that.
after.
I think you just have to search.
I already did, I already got.
Because the one on my
All I
computer
have
is
to do is
actually
just put it in.
because I haven't updated my systems last year.
Yeah,
So-
initially when I did it,
if I like
it's weird, and then I tried like different
Yeah.
sizes.
and I don't think I would like that.
Bro, mine just absolutely fucks. My bridge is fails.
It
It's completely falls apart.
So you can go, if you save in R1, you can open R2, but if you save in R2, you can't open.
Yeah, that's because I put a win for it.
And so it's-
And it totally buckles under sure.
Yes.
Yeah.
Why did you push it?
No,
I'm
unfortunately,
not,
I think
so
probably the
always,
easiest way would be to just uninstall Ansys from your laptop and then download and install the R1 student version.
Pressure from the boat.
I think
And then I
they still have that available.
reinforce it. I forgot which
Most
direction, but on
freely
one-
available software, they have version control.
Yeah,
And so
me
they
too.
you should be able to.
Yeah, so
I haven't tried it yet, but.
If you look here, this is like,
But that's.
it's a
that's probably
deformation
not-
of 17.
Yeah, it is annoying, because
millimeters.
the newest ones are two, and these ones haven't been.
See, why does yours look like that?
So we're not gonna update these until the summer. unfortunately.
I mean, well, your
Yeah.
force is extremely high, but what's your,
Test, so.
or your pressure is super high to have 5 megapascals on
Well,
the
I'm
full
assuming-
thing.
I'm assuming,
Bring
there's
all
a-
the
I'm assuming there's a point load for
boundaries
4
condition
tires.
first, and then
Let me see.
in order for the conversion.
If I got
and
a,
the real simulation.
No, what's your,
The quantum conditions
no, your code.
in the real simulation and the ones
this is
in the
equivalent.
conversion test.
Wait, let me see, let me see. your,
Yes. All, everything is, the only thing you're changing is just the mesh. density.
Yeah, those are my- yeah. So down, pressure load down this way and the pressure load this way, and then I have that displacement.
So is this the solid?
This is a solid, yeah.
Okay, yeah, a lot of people are getting that. If you're getting that,
Is it
error,
going on the
that's fine.
inside
So
of the
just
face
stop,
of the bridge?
just stop here and just say that I ran into this error because the
the
solid mesh, this
Oh,
one's
look.
really hard to do the solid mesh. honestly.
Pressure here.
I'm actually surprised at the number of
It's on
people
the
who actually,
Yeah,
I'm more
bro,
surprised at the
I
amount of people
put
who are actually able to do it
0.05
versus the amount of people who haven't.
Oh, my. rig-
And so I was able to do it just by tinkering with it like a lot and kind of seeing where.
So,
you know, where I
how'd
had
you
some
get it to be
mistakes,
kilowatts?
find there. And so I don't know if people who succeeded are
I
doing
think
that.
mine's 0.05.
Yeah, so I think
That's
it's
negative
probably,
too, right?
it's probably in the
And then I have
middle.
a
That's,
force
um,
of 15.
or actually it might be here, because what this error is basically
So
saying, is
15
one
kilonewtons.
element is thickness.
Yeah, just because
in
it's like,
one
I'm
direction
doing like the
and
force
two
of the
directions.
weight. Yeah,
So
bro,
it's either somewhere here or maybe on the beam at the top.
661 megapascals.
It's one of those.
661 megapascals.
You can,
350.
see, it's just a warning.
It doesn't say it
So a
has to
warning is
not
not gonna
fail,
stop
it
you.
just
It's not
says,
gonna
does
stop
it
you.
fail or not under the load?
It's just gonna say that, maybe you might want to calculate this.
What's yours?
And so if you get that, that's
Gotta be
actually,
pretty
that's actually exactly what I would. teach
Like,
you.
look at my deformation.
And so, just go ahead and.
Look at my
report that.
deformation field.
That's fine.
I'm getting my
Yeah,
max
not- not-
deformation
not-
here.
I mean, some people definitely be getting this, but not enough.
I'm getting my max deformation.
It's interesting, it's
here.
interesting to see how many people have not.
And then like the load deforms it.
Usually you won't get it if you have a small.
It's mostly here.
Yes, yeah, if you make a small element size, you can do
Yeah,
it.
'cause I have
But
a-
then with this one, I think if you make the element size smaller, you're gonna run the element count up just
Yeah.
by a ton, and you just can't. work from there.
So we're gonna report that.
This is exactly what I wanted.
Okay, cool. Also, I didn't have a question on this, but in classes when I graduated.
Okay.
I was wondering if you are, so you're teaching skills and trades.
Correct.
That's the semester.
Correct.
Is that
Under
something you
given the
teach
given
every fall?
condition 350.
So it's a brand new class, so this is all the first time actually.
Bro,
Mine didn't do, man. And honestly, the interest in it.
19,000 megapascals, that's even worse.
So I am under. So I don't know.
Bro, you put lives in this with this design.
Like
I didn't design
class
it.
last-
I didn't know.
That was actually pretty popular. Actually, that
Oh,
was
sorry,
teaching
you're
full
faulty.
computing.
So right now, as of
Killed
right now, we're
multiple
not
truck
planning on
drivers in a
teaching it.
family of six.
And so it's not on the schedule, but I did request. Because usually they add more technical electives, they add more formula level classes, and so I did say that if they want to do it, but I haven't heard back from the, yeah. Okay. Yeah, so it's called, computational, computational cardiovascular.
What are you gonna take next semester?
I made the class.
I'm gonna take 541 for sure.
Something like that. So basically what we do is,
What else? Are you gonna
we
take
actually use
anything
final
for high level?
analysis, but we don't use ANSYS, we use, a research software that I use called Simvascular. And we do simulations of blood. So I think it's really cool. And so there was a lot of interest in it. So
I don't wanna
that
take
one,
that
I say that
so
one's gonna be more likely. Biomechanics, I don't know. I think from a program
I wanna
standpoint,
try to take.
and kind of the reason I
materials.
proposed class.
There's no way
biomechanics
I'm taking that 530.
It's a good technical
No
lecture
way.
to have, just because it's kind of fundamental biomechanics. And
I'm
more
I
like to do
swear to
it.
God, yeah, I took 430.
But I don't know how.
I would, I know I
it's gonna depend
don't
on the
need to,
job.
but I would like to take it, because I wanna know about.
So I
partial
wouldn't, I
differentials.
don't want to make any.
But if there is
promises,
even a
I do- I
slight
would-
chance
I do
that
wanna
Dr.
keep-
Weiss is teaching that
But
class,
it's gonna depend on how.
I would never.
Okay.
Never,
One more question.
never.
Yep.
I know we're taking this one computer applications.
Yes,
Is this 5.1?
Yeah.
Is that like the next level or the next step after this class?
it's different. And so, and it's gonna depend on who teaches it. And so with these grad classes, a lot of it depends on who's teaching it and how they.
How many?
I'd say at this point, I'm probably most likely to use
How many,
5.1. And the way I teach it is I teach it from theory.
Mine converged.
So this
at
class we're not
15
going to
millimeters,
theory.
So that was around.
And so 541, we're really going to go to theory, and we're basically going to learn.
15 millimeters was.
Did you do 10?
And that's going to be the final project.
Yeah, I think I
Implementing
went to 8, but 15 is where I started conversion.
functional finance stuff. Not,
Oh, dude,
not
I
anything
have
complicated that
mine.
we're
What
doing
is
here,
mine?
but just like kind of simple 2D stuff.
8.5.
And so it is.
Yeah, I
it is
mean,
here.
8.5.
So
Yeah,
I'd say 541 is a bit more traditional in terms of.
Yeah, I'm just keeping
You
it,
took a
I'm
final
just keeping it.
course. You know, like UCLA, you probably take something closer to 540, because
Really?
they're teaching it from
Yeah.
the perspective
Like 2
that
minutes.
you're gonna develop your own color and work for ANSYS.
Is there a next step? after this
I'm
class?
tripping on 2 minutes?
Not really, and so I kind of teach it, you know, from the perspective that this is kind of the only ANSYS that you're gonna.
Was there on like?
This is definitely
10
the most
minutes?
advanced.
For me, it was for 10.
Yeah,
For me, it was 10.
At least in our, as far as.
Yeah, but I'm just keeping this.
So
I'm
the
just
kind of the
keeping this,
undergraduate version of this is
whatever it is,
410.
just because it's my last one.
And so we're doing 410, we're doing a lot of similar stuff,
I already calculated it.
but not.
I
to the
would just be
depth.
wasting company
And
resources.
so
if I was
actually, up
move
to
a
this
smaller
point,
match.
the two classes are mostly the same. The 410 at this point is going to diverge out with a little bit very light theory stuff. Whereas we're.
So you're gonna take Katia if you can get it?
We're doing
Yeah.
transient stuff, so we're gonna do modal simulations, we're gonna do.
I'm for sure taking
optimization.
541. I've been trying to
So
take
that's
a
kind of the
class
plan
for
for
2
us.
semesters now called failure of
But yeah,
materials.
410 kind of stops at this point. It does, it goes a little bit harder, so I do a little bit of transient, a little bit of modal stuff.
But I'm trying to do more
But
mechanics and
not too
materials
bad.
classes. But and the thing is, I want to take
Yeah.
composite materials. But that's the class I dropped last semester because it was that professor who lectured exclusively on PowerPoint. and I just could not take it. I'm hoping that he's not teaching it again this upcoming semester, because if he is, I'll just drop it.
Ashutosh, are you still there?
I won't sit there.
Yes, sir.
Yeah, fair enough.
Especially I have a problem of solver pivot warnings.
Yeah. So
in
that
activity
usually
4.
happens when your structure is under constraint, and so you probably need to add some more. If you're having trouble with the displacement constraint, you can try adding a fixed constraint on that side.
Yeah, no, that's the only.
Yeah, give that a try, and then I think that should hopefully solve your issue.
Okay,
Right,
sir.
Raphael,
Will
on
you
your
be
question.
available tomorrow on office hours?
Wait, say again?
Will you be available tomorrow in office hours?
Yes.
So that if I have any problem, I can ask there.
Yeah. I'll be there tomorrow.
Put it on the inside just
Okay,
so.
thank you, sir.
Okay.
If I do-
Yeah, give it a try, and if you're having issues, just come to office hours tomorrow, and I'll help you out.
Okay.
Yep.
Thanks again.
All right, Raphael, so for the project, are we only allowed to apply loads and boundary conditions that we use on past assignments? No, you can use other stuff. And so if you want, I know people have been using like bearing loads, they've been using moments. And so definitely feel free to use kind of whatever you want. Yeah. And so if it's something we haven't covered in the class yet, then you might have to do a little bit of research online to see, how to properly apply those boundary conditions. But feel free, you can, the whole repertoire of ANSYS is available to you. So as long as it makes physical sense to you, then that's the only thing. Yeah. All right. So there's a question in the class. So I'll be right back.
I mean, you're asking me if we can put it anywhere else, and it kind of makes sense that those hold the whole, if you want. No, I think it makes sense personally to just put it on the bottom faces. It's not gonna be moving. It can't, bro, if it's fixed on the bottom faces, both of those are touching the ground. There's no way it's gonna translate.
And we don't need to, you're right, you're right. I'm thinking about it like in terms of datums. You know, you were talking like that. Remember like the end of SolidWorks, they tell you like some data EGME?
No.
It might be better.
We're gonna take solar.
Well, if you work somewhere where you're gonna that's certified, like I'm certified.
You might have to measure with respect to water, so we want to make sure.
And then, I mean, obviously the company. It's like drafting standards and shit.
Should I just use this 8.5 millimeter?
Why is it? Would you consider?
So the why direction work. Yeah. Yeah, so you have to use one. And I just be over wide. Yes. The only thing is.
That's probably good actually, because the lemon would be.
Yeah, bro, that's the most fire.
Yeah, it is the most.
They have both the edge here and the side.
People who hate on that shit, I just.
Oh,
I don't trust it. I don't trust it. That is the, like, bro, when you're hungover,
Yeah.
just
Oh, yeah.
popping around. Shit.
The whole.
Just like, man, like, all the person.
Want to move it? Or want to move it? Should we want to because it is.
I did biomechanics homework and I was doing some of this, but I couldn't get past that. On Sunday I was doing this, but I couldn't get past.
Right now,
I couldn't, I didn't know.
This is kind of long. And so this is basic. But because it's.
I took a motion.
Then it stands
For 470 here.
And so all you do is you have to.
So you're not gonna make it. I'm not access to that.
So once you move it up.
It's just like, it's honestly hard for me to put it to words. Yeah.
Okay, but am I tripping here? So I have a rush right now.
Okay, sounds good.
And then I text Dom on the housing because I'm concerned about that, right?
Yeah.
And then I buy the sizing on it as well, right?
Sure.
Start showing you whenever you have a chance.
Okay, let me close this.
Yeah, sir. First. So sizing.